Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed about this exponential growth of a population based on like a logistic growth of population, and we have discussed also the Malthus model where there is a nonlinear growth of population was existing, and there itself we have discussed about like stability condition and how this intrinsic growth rate is affected by this resources like concentration and all other stuffs. And also we have discussed like chemostat growth there. So, how this chemostat is acting for this cell culture technique, that is a cell culture technique means either it is a continuous culture medium or like batch culture medium. So, based on that we have solved some of this differential equation, and in the present lecture we will start about this stability and linearization of a system of ordinary differential equations. So, for this lecture first we will just go for a steady state solution of chemostat model, since in the last lecture we have discussed in detail about this chemostat model, and how we can just linearize the system, that we will also discuss here. Then in this system how this Jacobian comes to the picture and how Jacobian helps out to us to solve the system, that we will just discuss. Then we will just go for a stability analysis of chemostat model and its biological significance in mathematical assumptions, that we will also discuss. So, first if you will just go for a stability state or the steady state solution of chemostat, and we have just discussed that this chemostat model or like a Michale's maintain kinetic model, it is a concept of non-dimensionalization we have just used to simplify that model, and we have obtained like two system of first order and first degree equation in a nonlinear form there. So, that is why we have just written here as we got a system of two first order first degree linear ordinary differential equation. So, these two systems, especially if you will just go for a steady state solution of these two equations, so that can be written as like dn by dt equals to 0 and dc by dt equals to 0. And obviously after non-dimensionalization that equation has been reduced as like dn by dt equals to alpha 1 dn by dt, especially if you will just see, that can be written as like alpha 1 c by 1 plus c n minus n there, and also dc by dt it was written as like minus c by 1 plus c n minus c plus alpha 2. And if you will just find the steady state, this means that this number of population is not get changed with respect to time, then we can just put it as 0, and this concentration level, that is also like our resources, that is not also changed with respect to time, that we can just assume as 0 there. So, that is why these equations are written as alpha 1 c by 1 plus c n minus n equals to 0 and minus c by 1 plus c n minus c plus alpha 2 equals to 0. So, if you will just solve this first equation, then we can just rewrite this equation in the form of like n into alpha 1 c by 1 plus c minus 1, this equals to 0. Obviously, we can just say that this is n equals to 0 or alpha 1 c by 1 plus c, this equals to 1 there. So, this implies that either n equals to 0 or c equals to, if you will just solve this equation here, alpha 1 c by 1 plus c, which can be written as like 1 plus c by alpha 1 c, this equals to 1 here. So, obviously, I can just write this one as, this implies I can just write 1 plus c by c as alpha 1, and this implies that 1 by c plus 1 as alpha here, and 1 by c, this equals to alpha minus 1, hence c equals to 1 by alpha minus 1. So, that is why it is just written as c equals to 1 by alpha 1 minus 1 here. Sorry, I have just written missed here alpha 1. And for n equals to 0, if you will just put in the second equation here, then we can just find c equals to alpha 2. And if you will just put like c equals to 1 by alpha 1 minus 1, then the second equation will be reduced as n equals to alpha 1 alpha 2 minus alpha 1 by alpha 1 minus 1. It is just a simplification, now we have just made it. So, if you will just put directly these values, obviously this n value directly you can just get from this equation. So, if we will just proceed further, that we have now two steady states for this equation, that is a Michaelis Menten kinetic model. We will have first value n equals to 0. If you will just see here, for n equals to 0, we are just getting c equals to alpha 2, and for n equals to c equals to 1 by alpha 1 minus 1, we are just obtaining n equals to alpha 1 alpha 2 minus alpha 1 by alpha 1 minus 1. So, both these values I am just writing here. And if we will just input some conditions that for practical application oriented, or how practically it will just behave. So, we have to consider that alpha 1 should be greater than 1 and alpha 2 should be greater than 1 by alpha 1 minus 1. Why we are just choosing that one? In the next slides we can just prove that one or verify that one, why we are assuming in that form and what is its practical meaning. And in the previous lecture also we have just considered like alpha 1 is considered as a V by F K max, which should be considered as much less than 1 here also. Even if you can also generalize this one, that if we are just putting here like 1 by alpha 1 minus 1. So, if alpha 1 is less than 1 here, then we will have a negative quantity. So, this population level resource should be present there to get a positive quantity there, and that is why we have to assume that alpha 1 should be greater than 1. And second case, if you just see that alpha 2 we are just assuming here. So, alpha 2, if you just see from this relationship here, since 1 by alpha 1 minus 1, it is already we are just assuming as like alpha 1 greater than 1, definitely alpha 2 must be greater than 1 by alpha 1 minus 1. Since always we will have like a positive n value and a positive c value there to find this growth of this population. Neither we cannot have a like valid population dynamics there, since always we will have certain resources and certain population to find a growth rate. So, that cannot be that like population level or like resources cannot be negative or 0 at best, I can say. So, the next question is that what happens to the solution which starts near the steady state. Steady state means we are just finding a state or the critical level. So, that should be maintained if we will just go for like t tends to infinity. To study this behavior, we will go for linearization, since all these factors whatever we are just getting here, that is in nonlinear form here. And if we will just linearize the forcing functions about steady states, so that we can study the behavior of model after perturbing these steady state values. So, definitely if we will just perturb these values, it will have an influence, or after certain time we will have a fixed value that can be considered as the steady state values or the critical values. So, first we will discuss about this linearization of the system. Linearization is a method by which any general function is linearized about a specific point, so that the model can be studied with given small perturbation to the specific point. This means that if you just introduce a small error close to that point, that does not affect the solution process. So, that we will just consider for the linearization of or linearization of any like nonlinear terms in that method. So, there are several methods for linearizing the system, like Newton's linearization technique, Taylor series. So, especially we will use here a Taylor series in the linearization technique, since Taylor series is one of the basic methods to do this linearization. Suppose if we will just consider like a general system, and then we can just put our equations in the generalized system to get this linearization of our problem. So, that is why we have just considered a general system that is expressed in the form of x dash equals to f of x y, and y dash it is just expressed as g of x y here. And just to get these values at a point, like steady state will be achieved at a point. So, arbitrarily we are just assigning two values x and y, where we can just get a steady state solution or a steady state of the system can be achieved. So, if you just define suppose two new variables, that is capital X of t as small x minus our this steady state solution system in the x coordinate, that is as x of t minus x, and y of t is defined as y of t minus y. If you just follow this basic definition here, that is just written as like linearization is a method by which any general function is linearized about a specific point. Since our specific point we are just considering as x y here, and the model can be studied with given small perturbation to the specific point. If you just see here, so x of t, which can be written as capital X of t plus x, a small perturbation it is just added with this point. And similarly y of t, if you will just see, it is written as like capital Y of t plus y here. That is the small perturbation, it is just added with the solution process to get a linearized form. This means that this factor should not influence the complete solution in that system. Now linearize this function f equals to f of x y and g equals to g of x y about this point x y, which is considered as the steady state point. And if you will just write this differentiation of small x dash, this as capital X dash, which can represented as like, since we have just defined in the previous slide here x dash as capital F x y here, and y dash is written as a g of x y here. So definitely we are just replacing this x and this x by capital X plus italic x, and y is replaced by capital Y plus italic y. So there exists one difference, so I have just put it in this form here, so then you can just visualize all these things clearly. So if you just take a Taylor series expansion of this function, since a Taylor series function can be applicable when there is a neighborhood point where this function is continuous, and we can just expand it in Taylor series form. So we are just considering the small neighborhood point as like here as a capital X and capital Y here, and small x and small y are the like steady state point where we can just find this functional value solution. So that is why we can just use Taylor series function or the Taylor series expansion at that point. Especially the function should be differentiable at that point, neither we cannot use also Taylor series expansion. So that is why we have just written as f of x plus x, y plus y as like f of x y plus x is the small perturbed term there. So x into f x x y and y dot f y x y, and plus the higher order terms like the second order differentiation terms or third order differentiation term, that is just assumed as a higher order terms here. Similarly, if you will just write like a g of x plus x and y plus y as a g of x y plus x g x plus y g y, where g x and g y both are like a differentiable function at the point x y, with these higher order terms which can include like second order and third order or higher order terms. Since small x small y are very close to this steady state points, that is the perturbed terms like capital X and capital Y are very small. So these especially we are just assuming these are the neighborhood points. Neighborhood points means sometimes in mathematical sense we are just using as epsilon there. This can be written as like x plus epsilon and y plus like epsilon there. So if we will just neglect this epsilon terms here, that is capital X and capital Y here, then we are just living with the terms as f of capital X plus x, y plus y as f of x y plus x f x plus y f y, plus order of higher terms it can be neglected, since this capital X, all of these power terms it is just neglected, and all of these power terms for this y is also neglected here. The same thing it has happened also for this expansion. Since this italic x and italic y is the steady state of the system which is obtained by, if you just take this first order differences as equals to 0, then we will have a like a steady state. So that is why we are just assuming these points as f of x y equals to 0 and g of x y equals to 0 for steady state. And if you just put both of them equals to 0, this will also satisfy this italic x and italic y at f and g functions, which will take the 0 values. Since these are the neighborhood points, so we can just assume that at this point also these functions are taking also the 0 values. Since at the difference level, if you just take that can be just linearize the factors. So, the linearized equations, if you just write here, we have already that these terms are equals to 0, these terms are equals to 0, we have left with like f of x plus x, y plus y, g of x plus x, y plus y, this equals to x f x plus y f y, x g x plus y g y, that we have just represented here. And in a matrix form, if you just write here, so this is nothing but we have just written there that as like x and y dash. So, that is why this x dash and y dash especially we can just write as x prime here. So, that is why the right hand side it can be expressed as a matrix A into matrix X, where matrix X can be represented as, since x and y it is just involved for this equation there. So, that is why we can just write vector x as like x y and x prime as like x dash and y dash primes, and the Jacobian of this matrix A can be written as like A equals to first f x, then f y, then g x and g y. If completely it will be multiplied with these factors like x and y. So, obviously this will just give you this vector there. And to find this eigenvalues of this matrix, to determine this whether this system is like a stable solution or unstable solution, we have to find the eigenvalues. Already we have discussed in the previous lectures that these eigenvalues of matrix A are given by like a determinant of A minus lambda equals to 0, and the system will be called stable if all of these eigenvalues of this matrix A are negative. Since we will have like a e to the power minus lambda x which will converts towards the 0 value. So, that is why it can have a like stable value, and if it will be exponentially growth, this means lambda is positive there, then we cannot have a like stable solution. So, if we will just go for our generalized model for this chemostat model to check the stability, the chemostat model already we have defined in our earlier lecture that dn by dt it is just written as alpha 1 c by 1 plus c n minus n, and dc by dt which is written as minus c by 1 plus c n minus c plus alpha 2 here. And to get this terms for this Jacobian, we can just first differentiate, since this is nothing but we are just writing here n prime, this is nothing but c prime here, and this can be expressed as like f of so already we have defined that one here, that is f of x plus x and g of x. If you will just see here, that is f of x plus x and y plus y, and g of x plus x and y plus y, this one only f of x y and g of x y. This is f of x y, this is g of x y. So, to get this first term here, we will just differentiate del f by del n here, and to find this term here, we will just differentiate this one del f by del c here. Since if you just see here, that is just written as f x and f y here. So, that is why I have just written del f by del n and del f by del c. So, first differentiation with respect to a n, it will just provide you alpha 1 c by 1 plus c minus 1 here, and with respect to c, if you will just differentiate this one, that will just provide you, so this factor it will just goes to 0, and you can just find alpha 1 and this is n by 1 plus c square, and if you will just differentiate again this is g term with respect to first n, then you can just find this one as minus c by 1 plus c here, and if you will just differentiate g term with respect to c here, then you can just find this one as first term as minus n by 1 plus c whole square, and minus c, this will just give you minus 1 here. And the steady states of chemostat models we have just considered as like when n equals to 0, we will have like c equals to alpha 2, and when we have just assumed c equals to 1 by alpha 1 minus 1, it just provides the value of n as alpha 1 alpha 2 minus alpha 1 by alpha 1 minus 1 here. And if you just put these values like for steady state n c equals to 0 alpha 2, then this is Jacobian matrix whatever we have just to get it. So, directly if you just put here like n equals to 0, we will have like alpha 1 c by 1 plus c minus 1, this will just completely give you 0 value here, and if you just put like n equals to 0 here and alpha 2 for C. So, this will just give you alpha 2 by 1 plus alpha 2 minus will be there. So, this will just completely 0 and this will be minus 1 here. So, the same thing we have just written here, that is alpha 1 alpha 2 by 1 plus alpha 2 minus 1 0 and minus alpha 2 by 1 plus alpha 2 minus 1. And if you just see, this is nothing but a lower triangular matrix, and the eigenvalues of this lower triangular matrix is nothing but the elements present in the like principal diagonal entries of this Jacobian matrix. And the eigenvalues are especially we can just write it as directly as like alpha 1 alpha 2 by 1 plus alpha 2 minus 1 and minus 1, since these are the principal diagonal entries here, they are the eigenvalues here. Now, we will just check whether these eigenvalues are negative or positive, or it is just representing some like imaginary values. So, if you will just go for the checking of the sign of the eigenvalues here, the first factor it is just written as like alpha 1 alpha 2 by 1 plus alpha 2 minus 1 here. And if we will just see here, if it is negative, then the system is stable. Already I have explained that if we can just write this expression in the form of e to the power minus lambda t there. So, whenever we are just approaching towards like t tends to infinity, then it is just approaching towards 0 there. So, that is why it has like a stable solution, otherwise it will be unstable. So, if we will just use this relationship like whatever we have just discussed in the earlier slides here, that alpha 2 should be greater than 1 by alpha 1 minus 1, already we have discussed that one, yes, here alpha 2 is greater than 1 by alpha 1 minus 1 here. Then we can just find that whether this eigenvalue is representing a positive value or negative value here. So, if you just use this relationship that is in the form of alpha 2 is greater than 1 by alpha 1 minus 1 to check the sign of this eigenvalue of alpha 1 alpha 2 by 1 minus 1 plus alpha 2 minus 1, we have just do a little manipulation here, that is in the form of since alpha 2 is greater than 1 by alpha 1 minus 1, obviously we can just write 1 by alpha 2 is less than alpha 1 minus 1, and we can just write this one as like alpha 1 should be kept in the right hand side and 1 can be taken to the left hand side here, and we can just write alpha 2 plus 1 by alpha 2, this should be less than alpha 1, and again if you will just take like this fractions here, we can just write alpha 2 by alpha 2 plus 1, this should be greater than 1 by alpha 1, and again we will just multiply this alpha 1 both the sides, then we can just write alpha 1 alpha 2 by alpha 2 plus 1 is greater than 1. So, finally, we can just if you will just take all the factors to the left hand side, alpha 1 alpha 2 by alpha 2 plus 1 minus 1, this is greater than 0. And obviously, the factor we have just obtained here is alpha 1 alpha 2 by 1 plus alpha 2 minus 1, which is just representing a positive value, and hence the point will give you a unstable solution here. Unstable solution means obviously you can just find that since we are just considering n value as a 0 here, this means a total number of a population, that is like cells or any other structure, if it is 0, definitely we cannot find a model there, and it will just does not represent anything. So, further if you will just go for for NC values as like alpha 1 alpha 2 minus alpha 1 by alpha 1 minus 1 and 1 by alpha 1 minus 1. So, the representation of this Jacobian matrix whatever we have just represent here, that is alpha 1 c by 1 plus c minus 1 and alpha 1 n by 1 plus c whole square and minus c by 1 plus c minus n by 1 plus c whole square minus 1. So, all these factors c and n, it will be replaced by these factors here. Then we will have like 0 at the first entry and alpha 1 minus 1 into alpha 2 into alpha 1 minus 1 minus 1, and this factor will be like minus 1 by alpha 1 and this will be minus alpha 1 minus 1 by alpha 1 and alpha 2 into alpha 1 minus 1 here. And if we want to find the eigenvalue of this Jacobian matrix here, we have to subtract lambda from this vector minus lambda this vector, and the determinant should equals to 0. And if you will just take this determinant equals to 0, then the reduced form of this Jacobian matrix, this can be written as like lambda square plus k lambda plus k equals to 0, where k is the factor which is represented in the form of like alpha 1 minus 1 into alpha 2 into alpha 1 minus 1 by alpha 1 here. This is just a simple multiplication you have to do. That means that minus lambda into, you can just write minus alpha 1 minus 1 by alpha 1 into alpha 2 into alpha 1 minus 1 minus lambda. So, minus this will be just to give you plus value 1 by alpha 1 into alpha 1 minus 1 into alpha 2 into alpha 2 minus 1 this equals to 0, and from this you can just get this equation. And if you will just find these eigenvalues, this is a quadratic equation. So, it will just provide two roots here, that is a minus k plus or minus square root of k square minus 4k by 2 here, and the nature of eigenvalues will entirely depend on the value of k here. Since we have already assumed that alpha 1 is greater than 1 and alpha 2 should be greater than 1 by alpha 1 minus 1. So, if you put all these values here, alpha 1 is greater than 1. So, this will just give you a positive value here, and second one we have just assumed as alpha 2 is greater than 1 by alpha 1 minus 1. So, it should also be greater than like 1 by alpha 1 minus 1, it will be just cancel it out here, and this will be minus 1 here by alpha 1. So, definitely k is greater than 0. And if we will just go for like further analysis of this characteristic equation, it is a quadratic equation whose sum of the roots is like minus k and product of the roots is k here. Since for the quadratic equation, especially the roots, it can be like alpha plus alpha and beta. If you are the roots, then it can just represented as alpha plus beta equals to minus b by a, and alpha into beta equals to c by a, which is product form. So, if you will use that formula, definitely you can just get that sum of these roots is minus k here and product of these roots is k here. Since we have obtained k is greater than 0 with the substitution of alpha 1 greater than 1 and alpha 2 greater than 1 by alpha 1 minus 1. So, its two roots will always be negative, and hence the steady state is achieved at n and c values for n equals to alpha 1 minus alpha 2 minus alpha 1 by alpha 1 minus 1 and c as 1 by alpha 1 minus 1, which shows the stability at all the steps. Now, if we will just go back to the initial assumptions we have just considered, that is alpha 1 greater than 1 and alpha 2 greater than 1 by alpha 1 minus 1. The reason is that already I have explained that these assumptions is that neither resource concentration nor population level, it cannot be negative. So, if it will be negative, then we do not have like a population model there. If population will be there, then that will be growth. If there is no population, then there will be no growth. And if there is a food or resource, then the population will exist there. If there is no resources there, then the population will not exist also. This is the mathematical reason. Now, let us check their biological meaning, how it is just existing. So, if you just go for this biological meaning of alpha 1 greater than 1 here. So, consider first the assumption that alpha 1 equals to, it is assumed in the like last lecture we have just considered that as v by f k max here, which is greater than 1. Obviously, if you will just consider here 1 by k max, which should be less than volume by flux here or flow. So, from the previous lecture we have considered that is a k as the factor of a k max into c by k n plus c. So, that k n is just a constant parameter which is just taking the values like k will achieve as k max when k n equals to 0, and this is just taking like half of this k max factor when c equals to like k n equals to c there. So, this constant Kn is a constant as a Michaelis Menten kinetic model, and also the dimension of K of C is a 1 by time inverse especially we can say. Hence, the dimension of 1 by K max, if you will just see, that is nothing but time, or say the minimum time, that is sorry, the maximum time. Also, if you will just see this equation for like population balance modeling for the cell growth. So, there itself we have just started this model, n dash t it has written as like k into n of t, where k is the rate of like growth rate or decay rate, whatever it may be. But this change of population size, that depends on k, and after that also we have just considered like k as a factor of c, where c is the resources, and depending on that we have just developed that model. And sometimes we have just find that this doubling time means the initial population size, it will be just get doubled from the original size, and we have just find that the time level as achieved as ln2 by k. So, if we adjust this constant term ln2, then 1 by k max simply gives the maximum doubling time of the model. This means that we are just assuming ln2 is a constant and it has a fixed value, we know, and 1 by k we are just getting. So, this will just achieve the maximum level if we will just double this time period. Now, what does mean by V by f here? So, in a dimensional analysis way, if you just see that V by f is nothing but that will just give you also a time level there, that is nothing but 1 by k max. So, if we will just go for the visualization of V by f in a physical sense here, suppose we will just consider a tank which is containing suppose 100 liter of these concentrations, and the rate of efflux is suppose f as like 10 liter per minute. Then V by f, that is the total volume, and the flux out, it is just occurring in a ratio form. This signifies the amount of time for the tank to get completely flushed out. This means that if you will just consider the total amount of time it is required to flux out everything, then there is a culture should be grow up there. This cannot be possible. So, the biological meaning of inequality, that is 1 by k max, which represents the time which should be less than the time, that is V by f, that is the maximum doubling time of bacteria should be less than the flushing time of tanks. So, if there is no flush of like these concentrations, how this population level will grows it off. So, it is always required that the population level growing, it is required that there should be a flux of time, it is more. So, if this like the flushing time of the tank, it is more, then we can just find that the growth rate will be increased. So, neither we cannot find that this maximum doubling time of bacteria should always be less than that of flushing of time, which is obvious. So, obviously you can just think that if there is a flux out, then you can just find that there is a like a well mixture medium, and you can just find the growth rate. And if there is no flux it out, how this population level will just grow it off there. So, if you just go for this biological meaning of alpha 2 greater than 1 by alpha 1 minus 1 here. So, consider this assumptions like alpha 2 greater than 1 by alpha 1 minus 1. While calculating the steady states of this model, we define one of the steady states of the resource concentration as a C equals to suppose 1 by alpha 1 minus 1 here. To differentiate this C representing the steady state from original one, let us write this as suppose C here. And if you will just see that after non-dimensionalization of the model, we have just to get rid of the asterisk marks from all the variables. So, this C is nothing but C star here. And if you will just define here alpha 2, which is defined as like C0 by C1 here, and in non-dimensional process we are just putting C1 equals to Kn. On the last lecture slides, we have just kept C1 equals to Kn there, and hence this inequality for these assumptions, if you just put here like C0 is greater than Knc star here, since alpha 2 we are just writing C0 by C1, and alpha 2 is greater than 1 by alpha 1 minus 1, and C is representing the steady state for that one. So, that is why we are just writing here, that is alpha 2 is greater than 1 by alpha 1 minus 1 here, and alpha 2 is obviously written as C 0 by C 1 here, and this is just written as like C is written, and C is nothing but we are just putting as C star. So, that is why we can just write C 0 is greater than C star into C 1 here, and where we are just putting C 1 equals to k n. So, that is why this equals to C star into k n. And obviously, if you will just see here, C 1 C star is nothing but the original C before non-dimensionalization. So, C 0 must be greater than C, that is the initial resource concentration should be greater than the steady state value of resources. Obviously, if this population starts from the beginning, they will use these concentrations or like their food to grow up, and when they will reach the steady state, especially this concentration level will be less compared to the initial concentration level. So, that we want to just show it off why we have just considered alpha 2 is greater than 1 by alpha 1 minus 1. So, in this lecture we have discussed about the steady state solutions of a chemostat model. Then we have just linearized this model using Taylor series method, and for this linearization we have introduced also this Jacobian to find the stability of this system, and its role on stability that we have discussed, and then we have just discussed about the stability analysis of chemostat model and its biological meaning, where we have just used these assumptions. And up to now we have just discussed like different mathematical models like deterministic, stochastic, and at the beginning of the level we have discussed about discrete time system, which involves like differential equations in one parametric form, two parametric form we have discussed. Then in the continuous time system we have discussed here ordinary differential equations, we have not started about PDEs. And in the ordinary differential equation sense, first we have just discussed about growth of microorganism, that is based on Malthus model, how this doubling of time is we can calculate for this like double of this total population size or half of the population size. Then we have discussed about chemostat model and how we can just formulate a chemostat model and its non-dimensionalization of the equations. Then the steady state analysis of this chemostat model equations, and then its mathematical significance with its biological relevance we have discussed. And in the ordinary differential equation sense we have discussed like order of the ordinary differential equations, degree of the ordinary differential equation, that is general solutions, particular solutions or singular solutions. And we have discussed like different methods for the solution of ordinary differential equation, that is a method of separation of variables, homogeneous ordinary differential equations, linear equations like Bernoulli or Leibniz form. Then we have discussed the stability analysis depending on the eigenvalue problems for the system of equations. And for the linearization we have used like a Taylor series method, and this stability is checked using this Jacobian matrix method, and finally we have just tested how the system is stable for all negative eigenvalues of Jacobian. Thank you for listening this lecture.